Good evening, and welcome to the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technologies. It is 6 p.m., but participants are yet to join. So we'll wait for a few more minutes before we get started. Thank you. Good evening and welcome to week 12 of the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technologies. Uh, this course is taught by Professor Sajan Kapil, who is a member of the faculty of the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Till now, we have looked at laser beam based powder bed AM, and today we'll discuss the last two topics for this course, being electron beam based powder bed AM and binder jetting based powder bed AM. And in the course of uh, this discussion, we'll be looking at the working principles and subsystems, a typical process cycle for an electron beam melting machine, uh, the qualities of powder, its production methods, and what characteristics decide the final part quality, the scanning system types, challenges associated with electron beam based powder bed AM, and beam powder interaction. So, right now we are here in this tree. We were looking at powder additive manufacturing, and of course, there are two ways to deliver this powder to the system. They can either exist previously in the region to be printed in the form of a thin layer of powder, and such systems are called powder bed systems, and they can be fed dynamically into the system wherever required by some feeding mechanism, typically being carried by some pneumatic means such as a carrier gas. In powder bed AM, we have we are currently looking at energy beam based AM methods and have already looked at laser beam based additive methods, which can broadly be divided into selective laser sintering and selective laser melting. Of course, as we will recall, the primary difference between the two is the method of fusion. In the case of selective laser sintering, the powder particles are fused together by a sintering process, which is actually a solid state process controlled by diffusion of atoms across the powder particles. Typically, the temperatures which are achieved are between 50% of melting temperature to just uh, till the melting temperature, but never quite achieving or exceeding it. Whereas the other set of or the other class of methods may together be referred to as selective laser melting, where the incident energy to the system melts the powder feedstock and also will impart some degree of superheat to the system so that it is not just at the melting point but heated to some temperature above the melting point. However, for such powder bed based additive manufacturing, uh, we may also resort to other sort of energy beams apart from laser. And one key class of energy beams which has been emerging and is a very exciting piece of technology is electron beam based powder bed additive manufacturing, which we will be looking into today. The joining mechanism in this case is typically melting, as the name suggests. So, the name of the process itself being electron beam melting or EBM. So, here the material is fused together by melting and fusion, and I am not really aware of any commercial processes which resort to sintering, although such a thing is entirely possible. The powder material which is typically used in an EBM process has to be conductive and is typically metallic. The reason for it is that electrons must be transmitted through the powder bed, and for that they need to be conductive. Typically, metals are conductive, and that is the class of materials which has been explored to the greatest extent using this method. We'll be looking at the scanning system and see how the electron beam is scanned across the region to be printed. Powder delivery is typically from the top by using hoppers. Uh, we'll be looking into details. The powder recording system is pretty similar to laser beam based powder bed AM methods. So either using something like a doctor's blade or a roller or even some slot feeding type mechanism may be possible. We also looked at some other few other recording systems such as electrostatic recording. However, those are not typically used here. Most commonly, a recorder blade or a roller may be used. The build atmosphere will typically be a vacuum and not an inert gas. And the reason, as we already iterated several times, is because of the way that these electrons transfer energy to the target surface. Electrons are among the lightest known subatomic particles, and they transfer energy to the system by virtue of their kinetic energy. They are very light and they can be accelerated to great speeds, almost approaching the speed of light. When they, with such great momentum, collide with the target surface, they transmit this kinetic energy into the system, and which may manifest in the form of heat and may melt the target surface or the beam or the powder particles or the wire, whatever as the case may be. However, since these particles are so light, if in their path from emission to reaching the target surface, they encounter other heavy molecules, they may be scattered away and may not reach the target surface at the desired flux. And so, we must ensure that their path is clear, and this may only be ensured in vacuum. The build platform will typically be made of the same material as the powder which is being printed, or if not the same, at least a material which is metallurgically compatible, because we would want to ensure that there is sufficient fusion between the first layer and the build plate. Typically, this extent of fusion is characterized by the dilution ratio, which we have already looked at in some of the previous lectures, which is defined as the area uh, that, if you're looking at a cross section of the bead, it is defined as the area that got melted below the substrate divided by the total area of the melt zone, comprising of both the molten area of the substrate and the molten area of the bead. It may also be quantified in other terms, such as by just using the height instead of areas. And depending on the formulation you're choosing, it will give you some extent of dilution. Typically, dilution between 10 to 40% is recommended for metallic systems to ensure sound metallurgical properties and healthy mechanical properties of the built part. In this slide, the typical process cycle for an electron beam melting machine is summarized, and this term, electron beam melting or EBM, is the commercial powder bed fusion process developed by Arcam, which was originally a Swedish company, but I think now it has been acquired by GE. As we were discussing, in this case, the powder delivery is accomplished from the top using powder hoppers, and we have a pair of powder hoppers, one on each side. Once, depending on the layer thickness that is desired, a sufficient amount of powder will be dispensed by these hoppers uh, by some means, whether it is by vibration under the action of gravity or some other means. Typically, not pneumatic means, because once again, we want to ensure vacuum inside this printing system. Once that powder is dispensed, it will be spread out and distributed over the region to be printed using the rake or what may typically be a doctor's blade. And we see the build time, which will contain the part that is getting printed, and the stage will move down by the desired height in each pass, and printing will continue. We also see the electron beam gun at the top, and we are seeing multiple rays, few dotted and one solid, which may describe the motion of the ray across the printing surface. But as we saw in some of the videos that Professor Kapil shared during the lecture, often the scan speeds are so high that it is not uncommon, based on the camera system that you are using to view, or if you are even looking at somehow through our naked eyes using some protective system, it is not uncommon to notice or see that, or it will appear that there are multiple electron beams which are scanning the system. whereas in reality it will only be one beam which is scanning at very high velocities. Uh, During the printing of a single layer, uh, the first process is the dispensing of powder from one of the hoppers on either side, and then this powder is spread out using this doctor's blade. So say if in the previous layer, this was the height till which printing had occurred, and this the difference between the current layer height and the previous layer height denotes the desirable layer thickness H. Then after the previous layer got printed, the build platform moved down by the same distance H. A suitable amount of or a suitable quantity of powder was dispensed by this powder hopper on the right, and then the rake or the doctor's blade is now spreading this powder out evenly across the region to be printed. And since we have powder hoppers on both sides, uh, say for this pass, the powder was dispensed at position 1 and the rake moved from position, sorry about that, and the rake moved from position 1 to position 2 here. In the next pass, the powder may be dispensed on side 2 here, and the rake will move from left to right and so on, thereby saving process time. The spreading characteristics may also be different depending on the type of recoating system that we are using. So, as we may recall, if we are using something like a doctor's blade, we will be able to handle a larger quantity of powder per layer, or we may be able to spread a larger quantity of matter powder at a time compared to the use of roller. However, in the case of roller, we have an additional degree of freedom in terms of the rotation of the roller along with its translation. And depending on whether it's a counter rotation or a forward rotation, we can have different characteristics, which we'll discuss further in the rolling section, the recoating section. Once the powder layer is spread, there is a preheating cycle. And there are several things to notice here. First, what is the need for preheating? Typically, say for most engineering metals, a common example of which will be steel, the liquidus temperature of stainless steel is typically 1700 or 1720 odd Kelvin, whereas the ambient temperature is often closer to something like say 290 Kelvin or so. So there is almost some 1400 Kelvin difference between the melting temperature and the ambient temperature. Now, when we're starting to print, or say the system has completely cooled down and we are now about to print the next layer, the temperature which will be achieved on the top of the powder layer or in the powder layer will be at least the liquidus temperature and potentially even several hundred kelvins higher. And typically these powder layers are of thickness of the order of what, some 40 to 50 micrometers. So across thickness of 40 or 50 micrometers, we have on one end uh, superheat temperature of the liquid metal, and on the other end we have ambient temperature. So a very large temperature gradient exists across this small region. And if printing occurs under these conditions, it can lead to the generation of very severe type of residual stresses, which will then lead to crack and delamination of parts. To get rid of it, we resort to this preheating strategy, which is again something that was borrowed from welding, where uh, in several cases, to prevent the occurrence of residual stresses or to print or to weld difficult to weld materials, some preheating was applied. In this case, rather than using any external heating, say like some resistance or inductive type of heating, we use the same electron beam that prints to preheat the powder layer. And this is done by using a coarser or thicker beam of larger spot size compared to the spot size which will be used for printing. This is also apparent from the thickness of the laser beam shown in this figure compared to say the printing cycle. And this can be achieved in two ways. One, we can either, if the provision exists, we can simply use a different size of electron beam. Say if we can readily switch across apertures or something of that sort. so that we now have a coarser beam to scan the surface. Or second thing, we can defocus the beam and increase the beam spot size. Of course, a third approach can be to just use the same spot size but lower the power so that we are not really melting the powders, we are just heating it to some extent. But then using a larger spot size will ensure that we are able to scan the entire area in fewer number of passes. Of course, given the very high speeds of this process, it does not, in uh, terms of time saved, it will not really matter much. But to make the process as efficient as possible, it's better to just defocus the laser or use a larger spot size. Once the bed is preheated, we will go for melting or the printing cycle, where again we switch to the fine aperture beam uh, and print our features on the powder bed. And this cycle will continue till all the layers are printed. And once it's done, the build part will be removed from the printing stage. And this for this, the entire build volume containing the sintered part or the printed part and the unused powder along with the print bed will be taken out. This powder will be recovered by suitable means and in all probability will be reused. The part will be separated from the substrate using most typically something like a bandsaw cutter or a wire radium, and it can be further post-processed depending on the requirements. We also have some numbers for the typical process characteristics of this electron beam melting technology. The power can go up to 3 kilowatts, which would appear to be on the lower end compared to laser beam based powder bed AM. For powder bed, the powers are still low, typically of only 500 watt or lower. But for powder feed based DD, it can easily go up to 10 kilowatt or so. The currents in this case are typically between 1 to 50 milliamps. The scanning speed can be up to 10 power 4, uh, this is not millimeter, up to 10 power 4 meter per second. The input power is typically 150 kilovolts. The vacuum pressure, which is required and maintained inside the build chamber, is 5 into 10 power minus 5 millibar, which, if we will recall, is in the same range as the vacuum required in the working chamber of any electron microscope, such as an FESEM. Whereas in the gun chamber, the vacuum is much higher, typically of the order of 10 power minus 9 millibar or so. The layer thicknesses which are typically used in this process or the feature resolution is between 10 and 150 micrometers. The surface roughness of finished parts is around between 2 to 20 micrometers. For reference, what we call mirror finish is typically 1 micrometer or lower. And the beam diameter will typically be between 100 to 350 micrometers. Now we'll remember that in laser powder bed fusion, the beam diameters are often say of the order of 40 micrometer, 50 micrometer or so, whereas here even the minimum beam diameter is 100 micrometers. What is the reason and can it be decreased further? In the case of lasers, the laser beam is essentially a beam of photons uh, which are not charged particles, and so they can be compressed to a reasonably small width and without affecting the process characteristics. Electrons, on the other hand, are charged particles, and if by some focusing means, say electrostatic focusing or magnetic focusing, even if we are able to say confine a flux of electrons into a smaller into a region which is decreasing and keeps getting smaller, will not be able to go beyond a certain extent, which in this case is typically 100 micrometers, because after a point these electrons will come very close together, and because of their charge will start repelling each other very strongly, and physically it will not be possible to confine them any further. This slide summarizes some of the manufacturing methods for the powder feedstock, which is used in electron beam and other powder bed based AM processes. Of course, we have also looked at it in some detail, I think, in one of the previous sessions. But here we are, there we only covered the atomization processes. Here we also have the mechanical and chemical processes of powder production. First is pulverization, which is a purely mechanical method of powder manufacturing, in which case the bulk material is crushed and ground mechanically to form fine powder. The powder produced from this pulverization process is fine, albeit very irregular. And so the finished part may not have optimum characteristics. On the other hand, electrolysis is a purely chemical process of powder manufacturing in which two electrodes are placed inside suitable electrolyte and the anode is made of the required metal. Since it is a purely chemical process, very pure powder can be produced. And some of the powders which are commonly generated using this method are those of iron and copper. Uh, Straight away, we can see that some application scenarios of the two. In a case where we are not really bothered much with the finished part quality, and we are okay with using irregularly shaped particles, but driving down cost is our primary objective. We can use powders which have been generated from a pulverization-like process. Whereas if uh, powder quality is our top concern, and we are very much interested in maintaining very high quality of powder, great purity, sphericity, and ensuring that the finished part has optimum or superior properties, we can opt for powder which has been manufactured through chemical electrolysis. However, with the underlying understanding that the cost of the raw feedstock in this case will be very high. We have already looked at the atomization class of processes, chiefly looking at water atomization, gas atomization, and plasma atomization. In gas atomization, molten metal is converted into droplets, which further is solidified into the powder. And this process produces regular and spherical powders. As we already saw, if what happens is we are introducing molten droplets of the alloy or metal into a system, and then these droplets are, or this molten material is being broken up into very fine droplets using some method. In water atomization, it is say affected through a spray of water, which breaks the molten metal into very fine droplets. However, in this case, the powders which form are somewhat irregular and not very spherical in morphology. In gas atomization, the molten metal is broken into tiny droplets using jet of gas, and this gas will typically be some inert gas like nitrogen or argon. Again, depending on the quality of gas used, there may be some uptake by the powder particles, which will reflect later during printing. As we can see, here we have two collection chambers. There is one collection chamber at the bottom, which will typically collect the coarser particles. However, there will be some particles which will be so light that they can be carried by this inert gas and deposited here in this fine powder collection region. And so we will typically have two separate distributions of powder, one of the fine kind and the other of the coarse kind. In the case of plasma atomization, the feedstock is typically in the form of a wire, which is fed into the system and then melted using plasma torches. Then, over this very slightly longish chamber, the molten material is now subjected to sudden vacuum. And because of the action of this vacuum and the sudden drop in pressure, the molten metal now breaks up into tiny discrete droplets, which solidify to form the metal powder. The powders which are manufactured using plasma atomization are of the highest quality and tend to have the highest sphericity and good mechanical properties when built into parts. And it's also stated here that plasma atomization is best for the additive manufacturing process. And typically, it's the same feedstock or the same process used for generating feedstock that is used by RCAM as well. Please allow me a second. I'll just have a sip of water. However, irrespective of the process being used, whether it is some mechanical means, chemical means, or some atomization means, it is never entirely possible to get powder particles of uniform size. That is, say if from this graph that is given here, we can see that the mean is approximately around 60 micrometers. So it is never possible to get a batch of powder which will have all particles with diameters exactly 60 micrometers. There will always be a distribution. So we will have powder particles which are slightly larger than 60 and those which are slightly smaller than 60. Of course, among these, the highest fraction of powder particles will be very close to 60. While it is possible to control the distribution or width of this variation, it is not really feasible to have powder particles of only one given size, or even if it were somehow possible, the costs would be truly inhibitive, and such powder feedstock will not really be usable because of the very high costs. Uh, gas plasma atomization typically gives us the tightest control over this powder size distribution, and it goes down as we opt for other methods. On the right here, we also have what I think is a scanning electron microscope image of powder particles, uh, which I presume is the feedstock for the printing process. And here we see how there are few particles which are very nicely spherical, whereas others which have a more elongated shape. And again, what is obvious is that the wide distribution in sizes of these powder particles. How is the electron beam focused and how is it deflected? In most of the EV guns used in manufacturing, electrostatic field is used for extraction and acceleration of the electron beam, and magnetic fields are used for focusing, deflecting, and correction of the electron beam. And a schematic of such a method is shown here on the left, where we can see that the negatively charged cathode uh, is the target or is the source of the electrons. We have focusing electrodes. The positively charged anode will attract these electrons from the cathode, and so in this region, the focusing of the electron beam is done or accomplished using electrostatic means. Here, the electrons do accelerate, and the acceleration is related to the change in speed. Typically, their speed increases as they are traveling from the cathode to the anode. Once they cross the anode, the path of the beams is focused or defocused or it is deflected using electromagnetic means. And after crossing the anode, typically the change in speed of the electron particles will be minimal, and so the acceleration associated with their motion will mostly be in terms of change in direction. Equation 1 also gives the components of the Lorentz force, which is given as F equals Q into E plus V cross B, where Q is the charge of the electron particle, E is the strength of the electric field, V is the velocity of the particle, and B is the strength of the magnetic field. From the cathode to the anode, focusing is done by electrostatic force, and from anode to the target surface or required area by using electromagnetic forces. And in this first stage, as we already discussed, the magnitude of electrons' velocity increases due to electric field, and in the second stage, Only the direction of the velocity changes while the magnitude remains almost the same. The focal length is also related to the magnetic field by this equation given here, 1 by f equals pi e square a b naught square by 16 m e naught, or 1 by f is proportional to b naught square. Therefore, the focal length is inversely proportional to 1 by b naught square. Uh, Now let us look at the deflection of the electron beam. In an electron beam gun, the electrons are deflected by electromagnetic lenses, which generate again the force shown in equation 1, F equals Q into V cross B. To move the electron beam, where V is the total velocity of the electrons, Q is the charge on the electrons, and B is the strength of the magnetic field. For instance, in this case, the electron is moving from left to right. So the direction of V is as shown, and the beam is getting deflected by this angle theta upwards from the horizontal. So the strength or the direction of the magnetic field will be into the plane, so that B cross V, sorry, V cross B will be upwards. And essentially, since this force is continually acting over this length A, what is happening is at each stage, uh, some force is acting and deflecting the electron by some small angle. And the net effect of this is the total angle of deflection theta. And so, in a sense, this is somewhat similar to the centripetal forces, which keeps any body uh, in motion about a perfectly circular path with constant velocity. And this equivalence has been used to derive these equations here. Mv square by r equals qvb. And so the radius of this path of deflection can be found as equal to 2ev by qvb. If the angle theta is small, then tan theta is approximately equals to theta, and we can find the horizontal deflection x in terms of the other known process parameters. Here x is the deflection, L is the beam through distance, V is the acceleration voltage, B is the strength of the magnetic field in Tesla, and A is the width of the constant magnetic field. So we saw that the path of the electrons is deflected using magnetic fields. But how are these magnetic fields generated? They are generated using these deflection coils as shown here. And we have a pair of deflection coils for deflection along the x direction, and a second pair of deflection coils for deflecting the electron beam in the y direction. And by a suitable combination of both these x and y deflection coils, we can actuate the electron beam in the desired fashion. And as we already saw, because of the very high speeds, say of the order of 10 power 4 uh, meter per second, it's not necessary to just deflect this electron beam in a straight linear path, but we can also do various types of patterns, such as the one shown here, where we have this circular path, and then it may deflect or shift forward by a small distance and continue. Or we can have this bilinear path, which is also used in some of the other processes. Since this is also a beam-based method, where there will also be other associated defects, which are typically associated with the beam, such as change in diameter of the beam when beam is focused, under focused, and over focused. Second, when beam is focused or deflected far away from the optical axis, there will be a change in the cross section. And because of this change in cross sectional area, there will be a change in the energy intensity distribution, which can lead to changes in the print characteristics of the bead which is finally getting printed. Stigmators are the electromagnetic coils with multipoles which are used to correct electron beam shapes. And electron beam astigmatism occurs due to error in electron beam optical systems, some of which are misalignment between the electrodes, or there can be some interference between the electric and magnetic fields. With astigmatic aberration, the type of beam shape that we'll see is on the top here, where say this is, well, given that this is in the plane, I think it's best to say that where this is the place which is near the optical axis, and as we deflect either to the left or right, we are moving farther away from the optical axis. So directly below the optical axis, our beam has a perfectly circular shape as desired and typically used. But as we move away, we see that the aspect ratio changes and it takes on a more elliptical shape. And as we move further away, this astigmatation error can increase. Whereas with a corrected electron beam, while the area of cross section may indeed increase, the shape will not be distorted. The present slide summarizes some of the common challenges associated with electron beam based powder bed AM. The first is delamination, which occurs because of the large temperature gradients that we discussed. And here we can see that this delamination can occur either near the first layer, such as shown here, the first layer between the substrate and the part being built, close to the first layer, that is, say, in the second, third layers, and so on, or even further up. Or there can be the formation of uneven surfaces in case the energy density which we are giving to the system is inadequate for printing. There can be porosities, and as we discussed previously, porosities are typically of two types. One is gas induced. Uh, for molten metals, the solubility of gases such as hydrogen is higher compared to solid metals. So when these metals are molten, they tend to dissolve gas. But when the energy source moves away and the metal will solidify, this gas will get liberated in a mushy zone where some of the liquid is metal is still molten, where the rest of it is solidifying. This gas will get liberated from the solid and keep accumulating in the liquid until finally it will exceed the solubility of the liquid also, and then form these uh, spheres of gas. Later, when the gas is released from the system, these sphere-like voids are left behind, and these are called gas-induced porosities. They will typically be perfectly spherical, and even their sizes will be relatively small. The other class of pores are process-induced pores, such as lack of fusion pores, and they may be formed because of insufficient or partial melting, or because of other process-associated deficiencies. And the way to distinguish between gas-induced and process-induced pores is process-induced pores will typically be elongated and irregular, and they will be typically larger than gas-induced pores. There will also be some volumetric shrinkage associated with phase change, because we know in the case of metals, upon melting, the volume increases for the same mass of material, whereas upon solidification, there is a shrinkage. Some shrinkage may also occur because of the packing density and the say void or air which exists between the powder particles uh, before and after they're molten. Before they get melted, they're in the form of discrete particles with void spaces in between. As after melting, they may fuse together and there will be an apparent shrinkage. However, the most commonly encountered or most debilitating challenge associated with electron beam melting is that of powder smoking. And it is illustrated in this series of images here, which are taken 5 milliseconds apart. Uh, we see this glowing powder at t equals to 5 milliseconds, and then this almost spatter-like behavior where we see some powder getting ejected from the surface and rest of it spreading around. And as time progresses, we can see that this powder almost blows up and gets ejected away from the surface like fireworks or in an explosive fashion. What is the reason for this? So, if we are assuming just a plain spherical model of powder particles, then in a powder bed, they will typically be connected to each other only at these small regions of contact across powders, which will be a non-conformal region, typically a surface, but still a very small contact. And we know that electric resistance is inversely proportional to area. So if the area of contact across two particles is very small, the electric resistance between them will be higher. When the system or the layer of powders is bombarded with this electron beam, they tend to get accumulated in, say, a bulk system where we are just assuming a continuum approach. These electrons would have flowed through the conductive material and spread out evenly, whereas because of this discrete nature of the powder bed and the very small contact between discrete particles, they tend to get accumulated on the say right below or in the region surrounding the electron beam. And once there is sufficient buildup of charge, the powder particles will start repelling each other. And because of the high flux, this process can be very quick. As we can see here, it's occurring across few milliseconds of time. And the charged powder particles can be explosively ejected from the surface. As we can see at the end, there is no powder remaining on the surface of the build plate, and so no printing will occur. This is typically referred to as spreading or smoking or the pushing of powder. And the reasons which have been identified for it are the presence of water residue or humidity, which later vaporizes as explosive because, as we know, when water uh, gets vaporized, it converts to steam and expands significantly in volume. If this expansion is not controlled, it can have an explosion-like effect. Uh, it may also happen because the momentum of the incident or incoming electron particles is greater than the cohesive force of powder particles which holds them together. But most importantly, it is because of the electrostatic charge buildup on the powder particles in the powder bed layer. The reason behind this electrostatic charge buildup are because of the pointwise or non-conformal connection between the particles, and second, because of the formation of oxide layers, which is very common for powder particles because of their high specific surface area. Uh, a few methods to mitigate or prevent this smoking phenomenon have also been proposed. One is the preheating or almost sintering of powder particles, which is done by RCAM already. Second is by changing the process parameters in terms of the current density, the beam size, and others. And third is by adopting suitable scan strategies, which can be optimized. The present state also summarizes the typical melt pool shape which forms under the action of an electron beam. And we can see that it is slightly different from the melt pool, which is typically accompanies a laser beam. And that is because of this small bulging regions to the sides. We see that in between there is almost this uniform region of constant thickness, but towards the ends there is this bulge, and the reason for that bulge is the nature of the electron and material interaction. So from all the electrons uh, that are bombarding the surface, some fraction will get transmitted through this first layer, denoted as layer 1 of height dz, and that fraction is shown as eta t1, whereas a small fraction eta b1 will get elastically backscattered and leave the surface. These backscattered electrons may then be captured and used to characterize the properties of this material near to the surface. Of the fraction of electrons which go through this or get transmitted through this first layer, some may again get elastically backscattered and get embedded in the first layer, now denoted by eta b2, whereas uh, a fraction of it may again transmit, denoted as eta t2, and this process continues. As we keep going deeper into the material, the radius of spread of these backscattered electrons also increases, which leads to this bulging or onion-like shape. Till finally, in approximately four layers, all the electrons are now trapped and embedded, and the melt pool ceases. This is also captured by the transition in fractions of eta t and eta b with increase in depth. And this penetration depth mainly will depend on the acceleration voltage and the density of the material. Of course, at all times, the fractions will obey this constitutive relationship eta A plus eta B plus eta T, because one, that is the fraction of electrons which get embedded in the given layer plus those which get backscattered from that given layer plus those which get transmitted from that given layer will always equal 1. And that was it for the electron beam based powder bed AM process. Now let us look at binder based powder bed AM process. And for this, we'll be looking at the working principles and subsystems, the powder and ink materials, the scanning system in binder based powder bed AM, the powder delivery system, the powder recoating system, some of the binder jetting based 3D printing technologies such as sand printing and metal printing, and then some very revolutionary and interesting thought provoking applications such as timed delivery of drugs and modeling of the printing process. So we have now covered almost all the methods under powder additive manufacturing, and we are dealing with the last one, which is the binder based powder bed AM. Again, we see that the schematic of the binder jetting machine, which in this case has been shown to be pretty similar to other powder bed based AM machines. The powder material which can typically be processed using binder jetting ranges across a wide variety of materials. It can process metals, ceramics, polymers, or even a combination of these into a multi-material. The scanning system consists of this deposition head, which will have single or more commonly multiple nozzles through which the binder material will be jetted out. The powder delivery system will again be mostly from the bottom. The powder recoating system will similarly be using a recoater blade or a roller. Build atmosphere will typically be like ambient. It will be open to atmosphere, and it is one of the
advantages associated with this process, and the built material will be similar to other powder bed based AM processes. In fact, in some cases, it may also be flexible to ensure easy removal of the printed part, or yeah, the printed part from this build substrate. So as we discussed, this process is capable of processing ceramics, polymers, metals, and any combination of these as either the powder material or the ink material. In fact, some 30 to 50% of the material which is printed using this process may be delivered through the ink itself. The scanning system can either consist of a single nozzle or more commonly of several multiple nozzles. The powder delivery system can either be a top feeding or a bottom feeding design. The schematic which we just saw had a bottom feeding powder delivery system. The powder recoating system will either be available in the form of a doctor's blade or in the form of a roller, which will have the additional degree of freedom of rotation about its own axis, or it can also be delivered using a slot feeder. The binder-based powder bed AM process offers wide choices of powder and binder material combinations. The binder can further be mixed with other materials. Further, dif materials of different color or different properties can be dispensed by different printheads of the same jetting head. Thus, binder-based powder bed AM can exercise control over the local material composition and help in the production of functionally graded materials or FGMs. Material can also be dispensed from the binder in liquid fashion, or it can be applied as molten matter. The proper placement of droplets can be used to create surfaces of controlled texture and to control the internal microstructure of the printed part. Binder-based powder bedding again has a unique flexibility that it can create parts of any geometry and out of almost any material, including ceramics, metals, polymers, composites, and multi-materials. It can also exercise local control over the material composition, microstructure, and surface texture. It is also readily scalable in production rate through the use of multiple nozzle technology, which has been commercially developed for printing images on paper. It just uses the inkjet technology, which is already available and well known to us. The types of material which are used for binder-based powder bed AM can be subdivided into whether the binding component is available in the ink itself, in the ink, or whether it is available in the powder itself and just getting activated by the use of the binder. If the binding component is present in the ink, the typical materials which are processed are powders, such as using a combination of ceramic metal or polymeric powders and inorganic or organic inks. Whereas if the binding component is already present in the powder and just needs to be activated using the binder material, then we can either use solvent inks such as polylactide or polycaprolactone, or we can use aqueous inks in conjunction with powders, which are starch, cellulose, plaster, or ionomer cements. The dispensing of this binder particle or binder droplets can either be continuous or drop on demand, and both of these technologies are further highlighted here through these schematics. We have a nozzle, and in the first case, it is continuously dispensing binder material at some given frequency, which is controlled by this drop ejection signal, which we see that is periodic in time. However, the binder may not be required at each and every location as the head is moving on the print region. And to control or prevent the transfer of these binder drops to the powder in regions where it is not required, we can have a deflection mechanism which transfers these droplets to a cup. So we can impart some electrostatic charge to the binder droplets so that they are negatively charged and the cup is positively charged, or vice versa. And for the regions where it is not required, we can activate this drop deflection signal so that the binder droplets are transferred to the cup, which may act as a reservoir, and the collected binder particles may be reused later and recycled. Or even better, we can just have a drop on demand type of system where the material is binder material is dispensed only over regions where it is explicitly required. And this drop on demand can be controlled using the nozzles. And irrespective of whether we need a single nozzle or we have multiple nozzles, it can be actuated using thermal or piezoelectric means. In the case of a thermal nozzle, we have this small plate here, which is connected to some electric supply, and it is heated. Upon heating, the binder material in its locality starts heating up and may even vaporize, leading to this formation of this bubble of vapor, which increases the pressure inside this nozzle and leads to the expulsion of a droplet of binder from this nozzle. Similar effects may also be obtained by using a piezoelectric, in which case the electric signal will lead to a mechanical deflection, and because of this deflection, the volume available in the nozzle chamber will decrease, and so to compensate the change in pressure, some amount of binder material will be dispensed out of the free end of the chamber. We also have a helpful table which contrasts and summarizes the differences between a thermal head and a piezoelectric head. A thermal head has typically lower cost and higher printing speed. However, because of the use of heating, it there is a risk of exposure of binder to thermal stresses, whereas there is no similar thermal exposure for the piezoelectric head. The droplets which are dispensed from thermal head typically tend to have a non-uniform size, whereas there is a far better control over droplet morphology in the case of piezoelectric head. And the droplets dispensed from a thermal head may not have very good directionality, as in it may not always fall vertically downwards. There may be small deflection, and so it must fall in the neighborhood of the region where it was exactly needed. Whereas piezoelectric dispensing heads tend to have good droplet directionality. Just like the other powder bed processes, the powder delivery system in this case may either be of the top feeding or bottom feeding type. Similarly, the recoating systems are also similar to previously encountered powder bed AM processes. We may have a doctor blade which can handle, say, a higher quantity or higher build rate of powder, whereas the rollers will typically have other advantages. If the direction of translation of the roller and the sense of its rotation are aligned, then it is called a forward rotating roller. And typically, this tends to have better packing density. Whereas if the sense of rotation is opposite to the direction of translation of the roller, uh, there is better flowability of the powder. Irrespective of the sense of rotation, roller type of recoating systems tend to have more uniform distribution or better spreading of the powder layer compared to blade-like systems. Of course, in certain situations, the slot feeder may also be preferable. And one of the earliest binder jetting type technology, 3D printing technology, was developed by Z Corp, and it started the name, or it was the first technology to use the name of 3D printing. This was developed at MIT, and the working principles were very similar to SLS, except that the binder liquid was sprayed in selected regions instead of a laser scanning those desirable regions. The raw material used was powder, and it can be used for the development of concept models very rapidly using a multijet multicolor spray over starch. The green parts will require sintering and in the as-built state will not have sufficient mechanical strength. When a binder is sprayed through thin nozzles on the selected region over a layer of powder, the particles in that region stick together, whereas the remaining particles which are not bound together are acting as support. The binder spray makes use of mechanical movement. However, multiple jets can make the process faster. The explicit support structures are typically not required because the surrounding unfused powder can act as support structure. In the case of selective laser melting, we still required support structures. However, the purpose was quite counterintuitive rather than to prevent the overhanging features from falling down. The reason in this case was to prevent them from warping upwards and colliding with the roller or other machine parts and damaging them. In this case, since the material is not experiencing such high temperatures and thermal gradients, the risk of warpage is almost non-existent, and so the need for support structures is almost eliminated altogether. They may still be required for some very critical sections or very large overhangs, but typically their need will be minimal. Of course, the greatest strength of this technology is that the wide gamut or the wide variety of powders which it can process. And it has been known by many names. Inkjet 3D printing, Z printing, because Z is typically the build direction, and it is a third dimension which distinguishes 2D printing from 3D printing, and of course the generic name of 3D printing itself. Z Corp's 3D printer was founded in December 94 by Marina H., Walter B., James B., and Timmy, based on a technology developed at MIT under the direction of Professor Elias. The company was sold to Contex and ultimately to 3D Systems in 2012. And here we have a few specifications of the Z Printer 150-250 set of machines. The resolution was 300 into 450 dpi, and this dpi is just dots per inch. And so it's very interesting and curious that the resolution here is expressed for a 3D printer in a manner similar to a 2D printer. The minimum feature size which could be printed was zero point 0.4 mm. The vertical build speed was 20 mm per hour, so very low. The build size was only 236 mm cross 185 mm cross 127 mm. And the typical materials which could be processed using this technology were starch and plaster formulation. And we can see a few colorful parts which have been printed using this technology. And some other binder-based powder bed AM technologies are those that print sand and also those which print metal using binder jetting. A very exciting and say practical real-world application of the binder jetting process is that of time delivery of drugs. Binder-based powder bed AM is a suitable process for producing time delivery drugs. This is because the process dispenses materials from two different sources. As we discussed, approximately 30% to 50% of the material can be dispensed from the binder or can be contained in the binder, whereas the remaining 70% to 50% can be contained in the powder. And because we have this flexibility of dispensing material from two different sources in the same process, we can, of course, give it very important applications. Tablets of various APIs with different shapes and release profiles have been developed using binder jetting, and the FDA approved Stratum was developed using binder jetting method by Zebros technology and Theriform technology. And here we have an outline. of how binder jetting based additive manufacturing can help in sustainable release of drugs into the patient's body. The rate of dissolution of any drug is proportional to the surface area of the tablet. So, the concentration of the drug shall be distributed such that the specified rate of drug is proportional to the conformal area. Based on this consideration, the concentration at conformal layers in close intervals is decided. So rather than having a uniform concentration of the drug molecule across the entire volume of the tablet, we can have a calculated variation in this concentration because we know that the drug will dissolve uh, uh, proportionally to the surface area. Originally, when the tablet is whole, its surface area is at its highest and the rate of dissolution is large. Later, as the tablet shrinks as it dissolves more and more, the available surface area also decreases, and so the rate of dissolution also decreases. Therefore, if we just uniformly distribute the concentration of drugs, we will, in the first, uh, say, while the surface area of the drug is still substantial, we will end up releasing a significant amount of drug into the patient's body. Whereas later, when most of it has dissolved and only a small amount of only a small amount of tablet is left, it will have a very small surface area, and so in the same amount of time, the amount of drug which is getting released into the patient's body has decreased substantially. And so, it is not wise or it is not the most optimum way to just distribute the drug concentration of drug uniformly into the tablet. Rather, it may be more helpful if we have some measured or compositional profile. This resulting gradient geometry is sliced into the horizontal layers, retaining the information of the relative concentration of the drug and the matrix. So after we come up with a variational concentration profile, we can program this into each layer. We can slice our tablet and then print it one layer at a time in each layer. We will have some variation in concentration. So here the variation is radially outwards. We can have a larger concentration near the center, which will have the smallest surface area surviving of the tablet, and a small concentration towards the edges where the surface area is more. And what this will ensure is that in every layer, while the drug is dispensed, its flow rate will be controlled so as to get the desired concentration, and the profile of release of drug into the patient's body will be almost linear with time. A second usage is that of multi-drug release. That is, it is also possible to load different or various drug molecules in different zones of the tablet, and such drugs can reduce the number of tablets required to be taken by the patient. Such as in the example shown here, we have this blue drug 2, embedded inside the pink drug or the larger drug 1. As the larger drug is getting dissolved with time, drug 1 is released, and when it is fully dissolved, drug 2 is exposed to the patient, and then it gets released with time. And this can be very helpful for those patients which may be required to take multiple drugs in a day, or say elderly people who are often required because of health complications to have multiple drugs, and it is an unpleasant experience. They can be saved effort, and sometimes out of forgetfulness also, they may forget to take a few of the medicines and their health may get adversely affected. And The use of such binder jetting technologies to combine multiple drug molecules into a single tablet may indeed prove revolutionary for such patients. With that, we have come to the conclusion of this week's course contents. So now let us just break for a very short while, and when we return, we'll look at some additional content on binder jetting and also few example problems which will be useful for solving the weekly assignments. So, good evening and welcome back. Let us now take a closer look at the binder jetting or binder based powder bed AM processes. And for this, I came across this really nice review article by Mustafi, which has been referenced here. And I just took a few sections out of it, which may enhance our understanding of the process. Here we have a schematic of the basic process cycles of a binder jetting based AM process. Of course, just like we already saw, first the print head will dispense the binder material selectively into the desirable regions, layer by layer. Uh, Once this is done, there will be a low temperature curing of the powder bed, approximately at 200 degrees Celsius or so. Then the bed will be depowdered and the cured parts will be extracted. At this stage, at 200 degrees Celsius, some of the binder material may also have been burnt off, and so uh, leading to the formation of voids inside this green part. And to fill up those voids and improve the density of the material, we use bronze infiltrate, or in some cases, copper infiltrate may also be used. And now the material is kept in contact with this infiltrate powder and kept in a sintering furnace at a far higher temperature for the sintering and infiltration process. Here, the bronze gets molten at sufficiently high temperatures and infiltrates into the voids left behind by the burning off of the binder through capillary reaction. Once this process is completed, the parts are sufficiently sintered, have sufficient density, and then the runners are removed and we obtain the final parts, which is a combination of both the infiltrate material and the build material, which may have been dispensed either through the powder bed itself or by mixing in the binder. This also reflects in the final color of the part, which is somewhat intermediate between the gray of the original powder and the bright yellow of the infiltrate material. Unlike other powder bed fusion technologies, binder jetting is compatible with virtually any powdered material. And because numerous powder materials and ceramics are sintered to full density in many current industries, binder jetting has a real potential to surpass PBF and have the widest selection of materials for all AM processes. Further, the shaping process occurs at room temperature and ambient atmosphere, avoiding issues related to oxidation, residual stress, elemental segregation, and phase changes, making the powders around the part in the build box highly recyclable, whereas previously we saw in the case of laser powder bed fusion, while the surrounding particle may not be getting molten or fused into the part which is getting built, it still experiences relatively high temperatures, which may lead to phase transformation and some sort of in situ heat treatment, thereby altering the properties of the part, uh, properties of the powder. Further, the powder particles may end up getting contaminated as they come in contact with the build chamber or the part which is getting built. And so, while they may be recycled, their properties will never be same as the properties of the nominal powder. The case in binder jetting is quite the opposite, where the powder is highly recyclable. Further, by avoiding the use of expensive seal chambers for vacuum or inerting, the build volume is among the largest compared with all AM technologies of the order of 2.2 meters into 1.2 meters into zero point 0.6 meters, while still maintaining a very high resolution afforded by inkjet, whereas previously we saw for other technologies such as powder feed based AM or warm, uh, the large or other processes with similarly large build chambers, that there was a trade-off in resolution. The resolution was not as high compared to powder bed processes, but then because of the requirement of vacuum in powder bed type processes, the build chambers were small. Uh, Binder setting combines the best of both worlds. In fusion-based AM, support materials must be produced alongside the part and attached to the build plate for stability, whereas in this case, the part is supported by loose powder in the job box. Further, no support structures are required. Then, fusion-based AM processes use a heat source for melting the layers of the powders, which may lead to the generation of residual stresses in the final product. In binder jetting, some heat is of course used during the post-processing and for lightly curing the binder, and because of the lack of significant heating or melting, binder jetted parts do not experience thermally induced stresses and distortions. Thus, fabricating overhanging features can be more practical. Again, compared with other powder bed fusion type techniques, binder jetting has high production rates and can produce large volumes of parts more cost effectively than other AM methods. Some of the major drawbacks of binder jetting include the multi-step nature of the process, in which post-processing steps are required, as printed parts show low relative density or close to 50%, and densification from this state usually results in significant distortion of the geometry. There is a higher surface roughness and lower resolution compared with some of the other powder bed fusion processes, and development of post-processing strategies uh, for most of the materials is still a work in progress. We have already looked at the powder morphology and the mean size and distribution. However, one or another important aspect which needs further consideration is the segregation, which is the separation of different sizes of powders in a mixture and is likely to occur in various steps, such as during feedstock preparation, during feeding the feedstock into the printer, while spreading the powder to build the final area using a roller. Some of the influential factors for segregation are the material, the handling, operation, and the environmental parameters. While handling powders, the powder must be remixed thoroughly. The hopper may be oscillated, followed by the roller compaction or a powder dispensing method using a roller. Further, this paper also provided some insights into the numerical modeling of binder jetting process. During the bonus live session, we already looked at numerical modeling of the fusion-based processes, such as powder bed AM, like powder bed fusion, or directed energy deposition, or wire and arc additive manufacturing. However, the treatment of binder jetting is slightly different because here, rather than say the application of a heat source and energy input to the system, uh, here binder is interacting with the powder material and leading to uh, say not fusion but uh, printing of the parts. So it's important to look into the numerical modeling aspects for the binder jetting or similar processes. This is still in its infancy, which offers scope for a lot of research, and a variety of challenges need to be tackled to enable more efficient and reliable simulations of binder jetting to assist the scientific understanding and engineering practice of this process. First and foremost, of course, being the modeling of the powder spreading, where typically the EM method or the discrete element modeling method, the DEM, has been widely used to predict the powder spreading process. The models, with certain calibration, can provide reasonable prediction regarding the general powder behavior during spreading, as well as packing density and surface roughness of the final powder bed. However, more understanding is needed for capturing the particle-particle interaction, especially when we are using non-ideal surface conditions such as rough, oxidized, or electrically discharged particles. Typically, in a modeling framework, we will just assume spherical or at best elliptical particles because they are mathematically easier to describe and more tractable. The effect of these conditions on the surface material properties and hence the particle-particle interaction forces should also be well understood and captured. Then there is the modeling of the binder and powder interaction. Whereas first, the current models for the dynamic wetting have been primarily focused on planar surfaces. In such processes as binder jetting, uh, the powder size is typically of the order of micrometer, and thus leading to very large surface curvatures. Thus, the theories which are applicable for planar surfaces may not be readily applicable to such highly curved powder surfaces. Second, the powder rearrangement and spattering driven by the binder impact is a critical physics which affects the green part quality. It should be considered in the process models to faithfully reflect the actual dynamics during binder jetting. Then there is modeling of the sintering process itself, where although the phase field method provides a powerful approach to simulate the kinetics of powder densification and grain growth, the phase field formulation has to be improved to be more thermodynamically consistent. Further, the phase field method is limited to very small domain sizes, whereas in the case of boundary jetting, what we saw is that the build volumes are easily of the meter scale. In this case specifically, the free energy density function and the relevant model parameters should have more explicit physical meaning and can be related directly to the actual material properties. Then there are some other aspects such as the powder quality. In terms of powder safety, powder materials have a high surface area to volume ratio, requiring extra attention when being handled. Flammability and explosivity are two key events to be aware of when working around powders of any kind, such as metal powders. Even food grains are combustible when in a cloud, which is why many explosivity safety standards exist in food grain processing. Powder material safety is an important topic for additive manufacturing because much can be learned from the uh, PM industry. AM introduces some new challenges in how machines are emptied of powder and how the powder is reused and stored. But still, storage, handling, and personal safety are well documented. Binder jetting has traditionally used non-reactive metals, and the equipment design reflects that in the sense that the setup is typically open to ambient atmosphere. Uh, there are no fumes, there are no high temperatures, there is no controlled atmosphere, no vacuum or purging with inert gases. Changing to reactive metals should prompt a safety assessment of the equipment to be used safely. Facility and personnel protective equipment should be borrowed from prior experience. The move to even smaller particles demands attention for the prevention of dust clouds, inhalation, and absorption via the skin, as well as facility protection to maintain a clean environment. Then there is the aspect of reactivity of powders. Metal powder has a high hazard potential due to the high burning temperatures and energy output upon combustion, such as the use of solid or aluminum powder for solid rocket fuels. Each metal has a level of reactivity related to its composition, and powdered metal further has a reactivity associated with the size distribution of the particles. Furthermore, whether the powder is settled in a pile, whether it is being moved, or whether it is dispersed in the form of a cloud, will change the reactivity potential. The US Bureau of Mines issued a report tracking the reactivity of a variety of powders with ignition temperatures, energies, and pressures for powders in cloud or settled form. And some such standards are also given here, such as NFPA 484, Chapter 4, Part 4.3, which deals with the determination of combustibility, and NFPA 484, Chapter 4, Part 4.4, which deals with the determination of explosivity. Here, NFPA is the National Fire Protection Agency of the United States. So, with this extra knowledge, now let us look into a few example problems which will be useful for solving the assignments for this week. Question 1 is asking us, why is a top feeding powder delivery system used in popular EB based powder bed AM? And some of the options given to us are A, to limit the chamber size, B, to ensure that vacuum is achieved in a reasonable time, C, because top powder delivery systems produce more uniform powder layers, or it is some combination of these options. Let us now examine these one by one. Will the use of top feeding powder delivery system limit the chamber size? Well, this is correct. Even in the slides, we saw how by the use of top feeding, the overall size and envelope of the machine can be significantly reduced compared to a machine with bottom feeding. Second, now that the envelope of the machine and the chamber size are reduced, the vacuum can also be achieved in a more reasonable time. For larger volumes, it will take a very long time to achieve vacuum of sufficient level. But the top powder delivery system did not produce more uniform powder layers. In fact, the uniformity of the powder layer which is spread will be controlled by the recoating process, whether we are using a doctor's blade or a slot type recoater or say a roller, and whether that roller has forward motion or uh, counterclockwise motion. And so option C is not correct. Both A and B are correct. The second question is asking us why are regular spherical shaped powders preferred for electron beam based powder bed additive manufacturing? And so the options given to us are that the spherical powders have improved flowability. Spherical powders tend to produce a uniform layer thickness after recoating. Spherical powders are easier and more economical to produce, or is it some combination of these options? Let us now consider each of these options one by one. Spherical powders have improved flowability. This is correct because of the regular shape and the smooth curvature. Their flowability is much better. They do tend to produce a uniform layer thickness after recoating, and we also saw how, because of the distribution of particles, uh, the small particles will settle in between the large ones, giving rise to a uh, uniform, uniformly thick layer with a decent packing density. However, to ensure the good sphericity requires more, say, cost input and higher or more sophisticated processes. Therefore, neither are they easier nor are they more economical to produce, and hence both options A and B are correct, while option C is wrong. The third question is asking us why is the scanning speed in electron beam based powder bed AM systems up to 3 orders of magnitude higher than a laser based system? We saw how for EBM the scanning speeds can be say of the order of 10 to the power 4 meter per second. And a few options are given to us. Is it because galvanometer has low but significant inertia, whereas there is no inertia in EV based systems? Is it because galvanometer mirrors are rotated using mirrors? Sorry, this should be motors. Whereas in electron beam based systems, electromagnetic coils deflect the electron beam dynamically. Is it because electron beam based powder bed AM is a more advanced and recent technology compared to laser based AM systems? Or is it some combination of these aforementioned options? Let us examine them one by one. Uh, the galvanometer has low but significant inertia, whereas there is no inertia in EV based systems. So, we have been discussing how in a galvanometer we have a pair of mirrors which are mounted onto motors, and by suitable deflection of these mirrors we are able to scan the laser beam all over the print bed. The mass and therefore the inertia associated with these mirrors is indeed low. However, it is not zero. Whereas in the case of electron beam based systems, there is simply no such mass inertia type consideration. And so option A is indeed correct. Galvanometer has low but significant inertia, whereas there is no inertia in EV based systems. Second, galvanometer mirrors are rotated using motors, which still requires some finite time and there will be some delay associated with or lag associated with the control logic. Whereas in EV based systems, the electromagnetic coils deflect the electron beam dynamically, which is a much faster process compared to the rotation of motors. However, the say more recent nature or being more sophisticated and advanced has nothing to do with the scan speed. And in fact, electron beam based welding may as well have been founded before laser based processes. And so options A and B are correct while C is wrong. Question 4 is asking us, a student proposes the idea of blown powder directed energy deposition using an electron beam as the energy source. What advantage will this technology provide over laser-based blown powder directed energy deposition? And the options given to us are, will it result in lower cost? Will it lead to higher production speeds? Will it lead to lower porosity of the finished parts? Or are none of the above true? Let us reread this question and try to catch what is up. The student is proposing the idea of blown powder directed energy deposition using an electron beam. However, we know that wherever an electron beam is associated, we will invariably need to have vacuum. The reason again being that electrons are among the lightest subatomic particles and they transfer energy to the target surface by virtue of their high kinetic energy. Since they are so light, they can be accelerated to very high velocities and upon collision with the target surface, they can transfer this kinetic energy to the surface, leading to a generation of heat and melting of the target surface. However, if in their path from the electron generator to the target, if they encounter any other heavy molecules, such as even air molecules, there is a very high chance that they will get scattered and a very small or insufficient flux of electrons will only reach the target, which will lead to not no melting or insufficient melting. The only way to ensure this and to clear the path of the electrons is to maintain vacuum in the chamber. And so, a blown powder DED process will invariably use some pneumatic mean, some pneumatic means of transferring this powder using a carrier gas, which will disrupt the vacuum, and so it will not be feasible. Thus, the process itself is not feasible. And option D is the correct option. Question 5 is asking us, why do binder based powder bed AM machines typically have no atmospheric control? Is it because of the low process temperatures? Is it because of the low to none chance of oxidation of powder particles? Is it because the addition of vacuum systems will increase the machine and process cost? Or is it because of a combination of few of these options? Let us consider each of these options one by one. In binder-based powder bed AM machines, indeed, the process temperatures which are encountered are pretty low. We may encounter slightly higher temperatures of the order of say few hundred degrees Celsius during the post-processing, sintering, infiltration, and so on. But the binder-based powder bed AM machines themselves are not exposed to such temperatures. They encounter ambient or close to ambient temperatures only. So option A is indeed correct. There are low process temperatures. Second, there is low to none chance of oxidation of powder particles because of the very low process temperatures. And so there is no need for maintaining a vacuum environment or purging of an inert gas because the materials are simply not exposed to high enough temperatures. They're at ambient temperature only. So unless the powder material is susceptible to corrosion or oxidation under ambient conditions, then there is no further chance of oxidation of powder particles during the binder-based powder bed AM process. So option B is also correct. Addition of vacuum system will increase the machine and process cost. While this statement is true in general, in the given context, this is not a reason why binder-based powder bed AM machines will not have atmospheric control. In fact, if it was required by the process, we would indeed have ensured that some such vacuum system or gas purging is associated and attached to the machine too, because our ultimate aim is to first print the part, and then we can think of ways and strategies to optimize the cost or bring them down or make the technology simpler and more accessible. And so both options A and B are correct. Question 6 is asking us, what are the advantages of binder jetting over other AM processes? And this is something where the review article which I cited may also prove useful, because we also saw a few points or a few advantages of this technology over other powder bed based AM processes. And a few statements are given to us, and we need to see which of them apply. Among the advantages of, or among the supposed advantages of binder jetting are listed: no residual stresses, no requirement of support structures, no need of environmental control, and a wide variety of materials can be processed. Option 1, no material, no residual stresses is indeed true, because in this case, we are only subjecting the powders to very low or close to ambient temperatures. Since there is no melting and solidification, there are no residual stresses involved. So statement 1 is correct. There is no requirement of support structures because the loose powder will already support any overhanging features. But additionally, such as in the case of laser powder bed fusion, where these support structures were needed to prevent the distortion of the part and to prevent its collision with the recoater during a recoating cycle. In this case, because there are no residual stresses and no, say, associated warping and distortion, there is almost zero requirement of support structures themselves. So statement 2 is also correct. There is no need of environmental control, which is something we just discussed in the previous question. And then the perhaps the greatest strength of binder jetting is that it can be used to process a very wide variety of materials. It can process almost any material ranging from metals to ceramics to polymers. So that would cover almost all the engineering materials. And then it can even process uh, combinations of them into multi-materials, while also controlling the local composition in the form of functionally graded materials. And so all of these four statements are correct. Thus, all of the above is the correct option to be chosen. And that was the last question for today, and indeed the last question for the live sessions of this course in general. So, with this, we have come to the end of today's session, as well as to the end of the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technology. It has been a pleasure and an absolute honor to assist the course participants during this course, and I hope it has been a learning experience for all of you and that I could add to your knowledge. Of course, the lectures delivered by Professor Kapil are more than sufficient to give a very holistic and complete view of the subject. Yet I have tried to add a few extra resources to pick your brains and to motivate you to think further and beyond the course material. It is my fervent hope that these sessions were useful to you and they help you in solving the assignments, as well as if some of you would have signed up for the course exam certification examinations, and then these sessions would prove useful there as well. I thoroughly enjoyed uh, preparing and delivering these sessions myself. And again, I would like to thank uh, NPTEL and Professor Kapil for this opportunity and the Prime Minister's Research Fellowship, which allows us fellows to undertake such exciting learning endeavors. With that, I would bid you guys adieu. And this is Sourav Goswami uh, from IIT Bombay. And I hope to see you again uh, in another course at another time. Thank you very much.